everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. Today would be the last lecture on Laplacian matrices. And in today's lecture, we'll try to figure out some interesting properties associated with the spectrum of a Laplacian for the case of undirected networks. We'll use the Gers-Corindas theorem to figure out where exactly some of the eigenvalues, or in fact, where exactly does the entire spectrum of the Laplacian lie, and can we use the spectrum of the Laplacian to figure out the degree of connectedness of the underlying graph. So let's get started and try to figure out how we can do all of these things. Before we start discussing the properties of Laplacian matrices, we'll do a quick recap of a result which we are going to use in today's lecture. Let's start with something that we know as the Gers-Corindas theorem. So what is the Gers-Corindas theorem? It says that let us consider any squared matrix P, which is, say, a real valued matrix. Then what always holds is that the spectrum of P belongs to or lies in a subset given by the union of a few disks. Let me quickly write it up. Union of I going from 1 to n, and we take the union of several disks. So we say Z is any complex valued number, then Z minus PII, the modulus of this must be, so this is the such that symbol. And the modulus of Z minus PII, let me bring it to the next line, is less than or equal to the summation of all of the off-diagonal entry. So this is the diagonal entry of the ith row. Then the summation of the off-diagonal entries, the absolute values of the off-diagonal entries, meaning write Pij, where j goes from 1 to n again, but is not equal to I. And then let's close this set symbol. Okay, so this is the Gers-Corindas theorem. It is indeed a very simple theorem. If we zoom into this part, so we say that Z belongs to C, meaning it's a complex number such that Z satisfies this condition. What does this condition imply? It implies that any Z that we choose must lie within a certain disk. What is that disk? We can write it here. So I will not go over it in a lot of details because we have already covered it in our previous lectures. But just for completion, let me write it. Every Gers-Corindas disk, or any Gers-Corindas disk for that matter, or let's write the ith Gers-Corindas disk. The ith Gers-Corindas disk is centered at PII and has a radius of this summation, which is nothing but the summation of all the off-diagonal entries. So we can draw multiple such disks in a space. So this can lie anywhere depending on the signs of PII. And then we simply say that each disk, we can just draw n number of disks here. Let me draw a proper disk here. So we can have multiple disks which are centered around or centered at. So let's say this is my P11, this could be my P1, P22, sorry. And similarly, I can have many such disks. And this could be slightly smaller, meaning I can draw like this, where this could be P33, and so on. Then all of the eigenvalues lie in the union of this space. And please remember there are n such disks, and we consider the union of all of the disks. So this is what the Kurz-Corin-Disk theorem says. What we'll do in today's lecture is try to figure out if we can use the Kurz-Corin-Disk theorem and then try to comment something on the spectral properties of the Laplacian. Can we say where exactly will the eigenvalues of a Laplacian lie? In the previous lecture, we talked about a few of the properties. For example, now we know what can we say about the graph structure if the eigenvalue 0 is repeated for a directed graph, and the eigenvalue of obviously the Laplacian. So now we talked about it in the previous lecture, but we talked specifically about the 0 eigenvalue. But do we know anything about the other eigenvalues? The answer to that question is yes, we can comment about it. And let's get started. So now we come back to the main theme, which is the Laplacian matrix. Before that, let me quickly remind you of what does a Laplacian always look like. Let's see. L11, L12, L1n, then we can write the ith row going up to Lin, and Ln2 going up to Lnn. Now, for a Laplacian, let us assume that the underlying network is underlying digraph is G, and the corresponding adjacency matrix is some A. Then I know that I can now substitute the Laplacian with the following values. L11 is simply equal to summation of L. Okay, in fact, first let's fill up the off-diagonal entries. It's slightly easier to do that. L12 is simply equal to A12, and the last entry is A1n. And this summation here is simply equal to the summation of A1j's where j goes from 1 to n, but is not equal to 1. So this is what it would look like. And similarly, for the ith entry, the first term would be ai1, ai2, and somewhere we will have this summation of the off-diagonal entries as the ith entry of the row. And similarly, the last entry would be ain. And for the last row, again, we'll have minus of an1, minus of an2. And now the last entry here will be the summation of anj, where j again varies from 1 to n and is not equal to I. So I know very specifically that any digraph that I choose, the Laplacian matrix for it will always take this form without fail. So now can I apply the Gers-Corinnes theorem and comment a few things about the Laplacian spectrum? The answer to that is yes. Let me take this ith row. The ith row of L has the following entries. Lii is again equal to summation of aij, where j varies from 1 to n, and j is not equal to I. And Lij is simply equal to minus of aij. So what do we observe here? We observe that Lii is always non-negative, right? And this here is obviously always non-positive. Let's try to construct the Gers-Corinnes theorem with this information. For the Gers-Corinnes disk, or rather, the ith Gers-Corinnes disk. The ith Gers-Corinnes disk has the following attributes. Its center is equal to Lii is equal to summation of aij, again j going from 1 to n, j not being equal to I. Let me write this here, aij. And what is the radius of the disk? Let me bring it here. The radius of the disk is simply the summation of all the off-diagonal entries. What happens when we sum this up? Remember that when we are summing it, we have to take, according to the Gers-Corinnes theorem, let me take you there. The radius of the disk is the summation of the absolute values of the off-diagonal entries. Meaning I have to take its absolute value, meaning this negative here gets removed. Why? Because we are assuming that all of the edge weights, whenever they exist, are strictly greater than 0. And if there's no edge, we treat aij to be equal to 0. But whenever there's an edge, this aij itself is greater than 0, meaning now this is equal to absolute value of minus aij, so I can directly write it as aij. Again, j goes from 1 to n, and j is not equal to I because we are summing up the off-diagonal entries. So what do we observe? We observe that the center and the radius, they take the same values, meaning now let's try to draw the ith Kerr-Scorin disk. With this information, the ith Kerr-Scorin disk will take this form. Let me shift it slightly here. It will be useful. Okay. Let me mark this point or this point here as the center. Let me call this some C and this is some R, the radius. Note that this is strictly greater than 0, or rather we can say greater than equal to 0. Hence, it is an RHP. And we know that R is equal to C, meaning this itself is my radius. So now if I draw the disk, it's going to take this shape. So the ith Kerr-Scorin disk will look like this. It's contained within this circle. This is the ith disk, right? Similarly, so this, let's again write it as Ci because it's the ith row, and Ri, which is equal to Ci. Meaning this here is I, this here is also I. Similarly, I can draw every other disk as well. But whatever I do, I must remember, let me first simply write down all of the centers. Maybe this is the ith center, perhaps. Let's say this is C1. In that case, my disk will have the same radius as this and will look something like this. Exactly this. And any other value I take, let's say C2 lies here, then I just have to take this disk. The radius just has to be the same. Meaning, eventually what we'll have is, we will get n such disks. First disk, second disk, and so on. Let's say this is our nth disk. Let's write this as Cn instead. So meaning, what do we get from this figure is that, I'll shift this here slightly. What we get is, whatever it is that we do, just a moment, so this point here is, let's say the nth center. So this way, what we can have is, we can have n number of disks. Let's say this is the first disk, this is some ith disk, and this is my nth disk. This is the ith disk, and this is the first disk. Notice that there's always a largest disk which contains every other disk. Obviously, this need not correspond to the nth disk itself. This, depending on the values of A11 to ANN, whichever has the largest value, that would correspond to the largest disk. Meaning, all of the eigenvalues are always contained within the largest disk. But the interesting point is, where does the largest disk lie? The largest disk lies in the right half plane. Implying all of the eigenvalues also lie in the right half plane. And we know that at least one of the eigenvalues is always equal to 0. So let's write up the observations based on this figure, or based on the Kerr-Scorin disk theorem. what can we say with certainty is that all the eigenvalues are non-negative. And we also know that we know from before that at least one eigenvalue is equal to 0. But this is a very important observation, meaning now I can write up my spectrum in this manner. Like I can always arrange them in a particular order. So in general, so let's pause with this observation. We will draw some more conclusions for a special class of digraphs or special class of graphs which are undirected. Up to this point, all of the results hold absolutely for any kind of graph. But now, let us consider the scenario when the graph that we have is actually undirected in nature. So we have established that whatever is the Laplacian, the eigenvalues are always non-negative. Now, let's discuss the special case of spectral properties for the special case of undirected graphs. Special properties of L, the Laplacian for undirected graphs. Are there any interesting properties? The answer is yes. There are some properties which are indeed interesting. That is, remember that, let's start writing. The Laplacian matrix for an undirected graph is a symmetric matrix. This implies all of its eigenvalues are real. So this is simply a property of symmetric matrices, that all of the eigenvalues are simply real. Then what are the properties that we already know? We know that according to the Gauss-Coriolis theorem, they are always positive. Now we also know that they are real valued, meaning instead of this disk, the region in which the eigenvalues can lie actually now condenses to the line R plus union 0, meaning that line is given by this. In general, for a Laplacian, it can lie here. However, for our case, it will lie within this itself. Meaning, what can we say? For an undirected graph, the eigenvalues first is lie in this range in general. The second property is Not only do the eigenvalues lie in this range, they can, or this interval, they can always be arranged in the following ascending order. Zero less than, actually this is lambda 1, lambda 2 going up to lambda n, where lambda 1 is always equal to 0. And rest of the eigenvalues, we simply know that they're real valued in the case of an undirected graph. And of course, these could be complex value when the graph is actually directed. However, either way, the real parts will still be positive in that case. The eigenvalue lambda 2, which is written here, which is the second smallest eigenvalue, not largest, second smallest eigenvalue. It reveals a lot of interesting properties about the connectedness of a graph, of an undirected graph. So what exactly are those properties? We'll call them as the algebraic connectivity of undirected graphs. The result that we have in this case says that for undirected graphs, the second smallest eigenvalue, lambda t, or let's write for a given undirected graph G, the second smallest eigenvalue lambda 2 is referred to or known as the algebraic connectivity of the graph G. Algebraic connectivity of G. But why is it referred to as the algebraic connectivity? The answer is this. Again, let's consider any undirected graph. Then let's highlight this as a result. The result here says that G is connected if and only if, so IFF stands for if and only if, lambda 2, the second smallest eigenvalue, is strictly greater than 0. So this is the first result. Let's call it result 1. It says that not only lambda 2 decides whether it is connected or not connected, we can figure out even more interesting results based on the zero eigenvalue, meaning suppose 0 is a repeated eigenvalue of L, then Suppose we can write lambda 2 less than lambda. This is some lambda I and it goes up to lambda n. Suppose this is equal to 0, lambda 2 is equal to 0, up to lambda I, all of them are equal to 0. And from lambda I plus 1, these are strictly positive. If this is the scenario, let's say, then we can arrange the spectrum as follows. And what does this imply? It implies that G has I number of disconnected components. Let's quickly look at an example of this very interesting result. Let's write an example. Let me quickly draw undirected graph here. And let's duplicate it further. Okay, and let me now quickly draw the edges. Suppose this is what my graph G looks like. Without even calculating the spectrum of the Laplacian, without even in fact calculating the Laplacian, I can draw the following conclusions. I can easily see that the number of disconnected components of G equals 3. This directly implies that the eigenvalue 0 of L is repeated thrice, meaning its algebraic multiplicity is equal to 3 thrice. In other words, suppose, or equivalently, if we had not been given this graph and only had been given this information, notice that the result that we have written here is also if and only if. If G has, let's write a double implies here, which would imply that if G has I number of disconnected components, then again it will have the eigenvalue 0 repeated I number of times. Meaning, if somebody just gives me this information that 0 is repeated thrice, then I know that the graph here will have 3 different connected components. Not only this, we can in fact conclude a few more properties. So here we assume the case that suppose 0 is a repeated eigenvalue. Now, let us consider the case when 0, say, may or may not be repeated. Meaning lambda 2, let's only say it is greater than equal to 0. Then we write the third result. The third result simply says the following. Consider two undirected graphs, G1 and G2 with adjacency matrices A1 and A2 respectively. Further, if, let's highlight this part, if A1 is less than or equal to A2, then the smallest eigenvalue lambda 2 of the Laplacian lambda 2 of L1 is also less than equal to lambda 2 of L2. What does this mean here? This is a very interesting property. It means that suppose A1 is less than equal to A2. When is it possible? It is possible under two cases. Let's just write the adjacency matrices. Then suppose these are the entries. Suppose these are the entries. Then the corresponding entries, let's mark them here again. Meaning entry-wise, if we take any entry here at the same position, whatever is the entry, has to be greater in value. Meaning two things can happen. Either for an edge existing in G1 and G2, the weight in G1 for that edge is less than equal to G2. Meaning from here, so here we say that the edge weight is greater than 0, or the other possibility is that G2 simply has more number of edges. More number of edges with the same or greater values of the edge weights. Values of the other edge weights. Other common edges of weights of the other common edges. By common edges, we mean that if we take any two vertices, maybe I and J, if there exists an edge here, then suppose there exists an edge here as well, then this edge weight has to be greater than equal to the one here. Or perhaps there does not exist an edge here, then there can also exist an edge. Meaning, one way or the other, lambda 2 is in fact a measure of how well connected a graph is. Meaning, higher the value of lambda 2, then there's a possibility of having a graph which has either a lot of edges, meaning it's very well connected, or the strength of connectivity is greater, meaning the edge weights have greater values. So this is how the spectral properties can actually reveal a lot of interesting topological properties of the underlying graph. So throughout this lecture, throughout the past few lectures, we have focused on the Laplacian matrix, and we dealt with the spectral properties of the Laplacian, and we say
And we realize that two specific eigenvalues are of very high importance. The first is the zero eigenvalue. The existence of the zero eigenvalue being repeated, meaning if its algebraic multiplicity is greater than 1, then for the undirected set of graphs, we can directly say that, let's summarize it. For the case of directed graphs, if algebraic multiplicity of the zero eigenvalue is greater than 1, then the digraph has multiple sinks, has more than one sinks. And what can we say about the undirected case? For the undirected case, if the algebraic multiplicity is greater than algebraic multiplicity of the zero eigenvalue of the Laplacian, of course, is greater than 1, then the graph has more than one disconnected components. Okay, with this, we will end today's lecture. And in the next lecture, we'll talk about yet another kind of fundamental matrix of a graph, which is very important, which is the incidence matrix. Thank you.